Okay, as I indicated to you the other day, today we will be beginning 8th grade math. However, anytime you begin something, you need a foundation for it. And so that's really what we're going to be doing today, is starting the building process towards the higher level material. And whether you're good at math or not doesn't really matter, but one nice thing about math relative to other academic classes is that it's a building process, and every new skill you learned is based on a skill you learned before. And so that's what we're going to try and get at in today's warm-up. Everything in today's warm-up is a skill that you're supposed to have achieved mastery level of. Let's see how well we've done. Number 1, give me a factor pair. Factor pair. Alexis, give me one of them. Okay, Kiara, give me another one. Well, that's the same one. Okay, well, I'm glad you brought that up. You don't have to flip it around. Once you say 1 times 7, it's implied that 7 times 1 is also a factor pair. So it's just repeating the same thing. And so I think your point is that there's only one factor pair, 1 times 7. What about number 2, the number 10? Give me a factor pair. Give me one of them. Natalie and then Annie. 2 times 5. 10 times 1. Angela? Okay. 1 times 10, 2 times 5. Number 3, the number 30. We'll start with Adriana, Savannah, and then Tatiana. Adriana, give me 1.
2 times 15.
Okay.
6 times 12.
Okay.
3 times 7.
Okay. We missing it? 1 times 30, and that's the one that should pop into your head first every time we do something like this. There's always 1 times itself. Very good. Any comments, questions about any of these 3 before we move on? Good. Now, divisibility. We're talking about whether or not this number is divisible by these numbers. And divisible means you divide and you end up with a whole number as a result. That's what divisibility is. So, what is 100,224 divisible by? Give me all of the numbers it's divisible by. David and then Stephen.
2, 3, 4, 6, and 9.
Okay, what do you think, Stephen?
2, 3, 4, 6, 9.
So you agree exactly with what David said? It is divisible by 2, 3, 4, 6, and 9. Unfortunately, if you're missing a number, it's wrong, and if you added in a number, it's wrong. Number 5, the number 789. Which numbers is that divisible by? We'll start with DeAndre, then Chelsea, and then Kiara. 3. Just 3. 3 and 9. So we do have some disagreement. What do you think, Amani? Just 3. It is just divisible by 3. What about number 6, the number 3,707? We'll start with Savannah, George, and then Adriana. No numbers. You all think that it's not divisible by any of these, and you would be correct. And interestingly enough, the activity in numbers 1, 2, and 3 is actually based on 4, 5, and 6. So these skills are closely related. I did give you some easy ones for numbers 1, 2, and 3, but if I asked you to come up with factor pairs with larger numbers, then you would have to do this skill down here. And does anyone remember when we learned this skill? Okay, you're about right, George. Yes, first day of school. First day of school. It's actually not in the textbook at all. Not in the textbook at all. But yet I felt it was so important that I needed it to be done first day of school. Because it was supposed to carry through the entire year, which it actually has. But now we're going to be using it again and again and again in a more obvious way. So let's quickly review. There are 3 divisibility rules that I would consider very easy, and I call them visual rules. Could someone remind us which numbers are the visual rules? Natalie? 2, 5, and 10. They all are visual rules. Angela, where do we look for 2, 5, and 10? The ones digit. You said that beautifully. We look at the ones digit. The rule for 2 says to do what? Rule for 2 says to do what? Stephen? Then it's divisible by 2. Very good. What about the rule for 5? Adriana?
Well, no. If it's a 5 or a 0.
Yeah, but you actually, the other way you said it was accurate, but it's a little easier for people to understand. Just look for a 5 or a 0. Okay, very good, and I like the way you corrected yourself. And what about the rule for 10? What does that tell us to do? Tristan? Very good, if the ones digit is a 0. And so you see that none of these numbers actually were divisible by 5 or 10. Very good. Now, the rules that were a little bit harder. The rule for 3 and the rule for 9 were very similar. What were the rules for that? Kiara? Okay, so let me change one word. You said add all the numbers. We add all the, what's the right word? Savannah? Digits, okay? But you're right, I knew what you meant. So you add all the digits. So let's look at number 4. 1 plus 0 plus 0 plus 2 plus 2 plus 4. What does that add up to? Alexis? It adds up to 9. Now check and see if 9 is divisible by 3. Yes, it is. Now check and see if 9 is divisible by 9. Yes, it is. And that is why it is divisible by 3 and 9. But let's now test out number 5, 789. Add those up. What does it come out to? Catalina? 24. Is 24 divisible by 3? Yes. You get 8. Is 24 divisible by 9? No, it is not. And that's why you only see a 3. Any comments, questions about the rules for 3 and 9? These are important rules. All right, the last 2 are probably the ones that are most forgotten, but they're not really that hard. Let's see who remembers the rule for 4. What is the rule for 4? You got 4 people? Go ahead, David, you're on a roll today.
The rule for 4 is you check the last 2 digits, and if they're divisible by 4, then the numbers are divisible.
Yeah, and what it really means is pretend that this is not here, and pretend that that's the number. Is 24 divisible by 4? Yes. That means that that number is divisible by 4. Is 89 divisible by 4? It's a hard one to tell, but I know 80 is divisible by 4. It just seems like it wouldn't be divisible, so I would say no. And in this one, is 07 divisible by 4? Clearly not. So that's the rule for 4. What's the rule for 6? What's the rule for 6? Chelsea? That's right. If a number is divisible by 2 and 3, then it is also divisible by 6. And that's why you always see them together. What's the connection between the numbers 2, 3, and 6? There seems like there should be a connection. Why is there? What's the connection? That's right. So 2 times 3 is 6. And guess what? Could we extend that idea to other numbers? Like, what if a number is divisible by 2 and 9? Could you give me another number that it's probably divisible by? Cameron? 18. Let's see if that works. Take calculator, take the number 100,224 divided by 18. Look at that, it works. I wonder, what about 3 times 4? Do you think this number is divisible by 12? let's see, 1. So now you actually have a very powerful tool at your disposal. Because sometimes you need to find a bigger number that something's divisible by. So now if it's divisible by 3 and it's divisible by 4, then you know it's divisible by 12 because 3 times 4 is 12. Very good. Anyone have any comments, questions, concerns on anything? Any comments or questions? Make sure you wrote down lesson 4.1. This is chapter 4. All right, so let's start today's lesson. There is going to be a bit of review. The title of today's lesson is prime factorization. So please write that down. That's a term you're going to need to be able to speak and discuss. Prime factorization. But we're going to talk about a couple of words, and you're not going to have to write down the definitions because you're supposed to already know them. Let's rewind for a second. Let's look at these top 3 questions. Can anyone tell us anything about these 3 numbers? The number 7, the number 10, the number 30? Nolly? Okay. You are absolutely correct. David, what were you going to say? Okay, so then could you explain how do we know that 7 is prime?
Well, because it only has 2 factors.
What are the 2 factors?
1 and 7.
1 and 7, that's right. And so when you have a number that only has 2 factors, 1 and itself, that is called a prime number. And then the opposite of that is if it has more than 2 factors, like the number 10 and 30, and you can clearly see all these factors. Each one of these numbers is a factor. 10 is a factor, 2 is a factor, 5 is a factor. Every number has a factor of 1 except for the number 0. Okay? So, those are the first 2 definitions. We don't need to copy them down because you already know them. You learned it last year, possibly the year before. A prime number is a whole number greater than 1 that has 2 factors. 1 in itself, a composite number is a number greater than 1 that has more than 2 factors. Anyone have any questions about that? That is the foundation of what we're going to be doing today. All right, a prime factorization. This is where we start possibly new material. Kind of depends on who your teacher was last year and your experiences in school for the last 2 years. Prime factorization is when you take a number and break it down into smaller pieces. And we want to break it down all the way to its prime factors. And then we write it out as a product or a multiplication problem. A product of prime factors. And this is one of our major goals today. Here's an example of what it will look like. 2 times 3 times 5 to the 2nd power. 2 is prime, 3 is prime, 5 is prime. If we multiply all these together, we will get a result. Okay? If you don't know what I'm talking about yet, don't worry about it. You will in a couple of minutes. A factor tree. You should have been introduced to it, but if you haven't, you'll see it today. You'll understand. A factor tree is a tool that we use to get to the prime factorization. For this class, being an advanced class, and I'd say highly advanced, our goal is to be able to accomplish this without using the tree eventually. You're going to do trees today, but our goal is to be able to do it without the tree, and I'll talk about that next time. Now, this concept is taught in regular 7th grade math. So how is regular 7th grade math different than pre-algebra or advanced 7th grade math? Well, this last idea is what separates us. A monomial. And here's where we're going to jump up the level of complexity to include algebra. A monomial is a number, a variable, or a product of a number and variable raised to whole number powers. So, I'm going to give you some examples, but here is a key word. Product, meaning multiplication. So I'm going to give you a few examples and a few non-examples. Here is a simple example of a monomial. 2x. 2x is a monomial. 2x plus 3 is not a monomial because there is an addition sign, and that makes it now it's called something else, and you don't have to worry about its name, but that's not a monomial. So this is a non-example. That's not a monomial. Here's another example of a monomial. 4z to the second power. That's a monomial. But 4z to the second power minus 8z is not a monomial. Once you connect terms with an addition or subtraction, that becomes something different. And the rules are completely different. It can be something even more complex, like 18x squared y to the third z to the 8th power. That is a monomial, because the only thing involved is multiplication. But if it was written like this, 18x squared plus y to the third plus z to the 8th, that is called something else. And that is something that we're not interested in right now. Does anyone have any questions so far about what a monomial is?
So it only applies to multiplication.
That's right. I had a student in one of my other classes say, well, what if I have two of them multiplied together? Like, what if I did 2x times 4z squared? Well, that's still a monomial because it's all being multiplied. So the deciding factor is the addition and subtraction signs. Okay? And so we're going to actually learn how to break these apart. We're going to learn how to do prime factorizations like this and of things like this. And that's what separates us from average math students. We're going to first start out with the concepts of prime and composite, and we're going to go extremely fast. So, example 1. Determining whether a number is prime or composite, we're going to go unbelievably fast. So take the number 63. I just want to know, is it prime or composite? So a long way would be to take the number, write it down, and try to find as many factor pairs as you could. We automatically know that 1 times 63 is a factor pair, but are there any others? Are there any others? Natalie? 7 times 9. Once you find another factor pair, then you already know that it's which type of number. Someone raise their hand and tell us. Which type? Kiara? This is composite. Very good. So you don't have to list anything else. If I'm just asking you whether it's prime or composite, you just need to do enough to know the difference. But this group is very advanced. So in your mind, you should be looking at this number and going through the divisibility rules. You should have immediately known that it was divisible by 3 and 9, because you should have mentally added 6 plus 3, that's 9. That's divisible by 3 and 9, you automatically know it's composite. Does anyone have any questions about that? So let's approach part B as advanced students. The number 29. Is it prime or composite? So you're mentally going through the divisibility rules. Is it divisible by 2? Is it divisible by 3, 4, 5, 6, 9, 10? What do you think, Kiara? You think it's prime? Can't find anything that is divisible by? George? You think it's prime? Yeah, this is not divisible by anything, so it is a prime number. Anyone have any comments, questions, concerns? Go ahead, Nala.
After you do the tree though, and you're
Yes, it would be. Don't worry about it right now, but yeah, you're right. All right, so we've done one concept, determining whether something is prime or composite. Let's see if you can do it on your own. Remember, checkpoints, you do not have to copy the original question. You just have to find me the answer. And I would consider this question very easy, so you got 30 seconds.
Do we have to?
Let's check this one by survey. Give me a thumbs up if you think it's prime. Give me a thumbs up if you think it's composite. Boy, I'm disappointed in myself. I didn't trick anybody. Good. Put your thumbs down. It is composite. What is it divisible by? Someone tell us what it's divisible by. Essence? 3 and 9, yeah. It's divisible by 3 and 9 if you add the digits. 1 plus 1 plus 7, you get 9. Very good. Any comments, questions, concerns? Good. I told you we were going to go fast, but now we're going to go a little bit slower, but not too much. Now we take it to the next level. Now that we can tell the difference between prime and composite, now we use that skill to find what's called a prime factorization. And we're going to do the number 420. Now, don't start yet because I'm going to be splitting the class in halves. We're going to do this prime factorization, this first one, we're going to do it twice. But I'm going to do it twice. You're going to do it twice with me, but you only have to write down one of them. Okay? So I'm going to do one in blue and one in green. Everyone from Catalina's column over to the cabinets, you guys are doing blue. Everyone from David's column over, you are copying the green one. You participate in both. I'm going to need a lot of volunteers for a lot of different things. You participate in both, but you only have to copy one. So I'm going to do 420 here, and we're going to draw a tree. Then I'm going to do 420 over here, and we're drawing a separate tree. And there's a reason why I'm doing it twice. You will see the reason at the end. You all participate in both. It doesn't matter which color I assigned you to copy, you still participate and pay attention to both. I need a factor pair for 420. A factor pair. Adriana? That would have been the one that popped in my mind first. 10 times 42. Very good. Now I need another factor pair for 42. It must be different. A different factor pair. Nolly? 210 times 2. Very good. Make sure you copy down the one I assigned you. So now, the goal is to end up with only prime numbers. So now we have to know the difference between prime and composite. Anytime I find a prime number, I'm going to circle it. You are going to circle it as well. When you circle the prime number, that means the branch is now closed. That closes the branch. So let me start with the blue. Is 10 prime? No. 42 prime? No. Because I'm doing the divisibility rules really fast in my head. So now that means I get more branches. The 10 is going to branch off, and the 42 is going to branch off. I need a factor pair for 10. Tatiana? 2 times 5. So I'm going to write a 2 and a 5, and I need a factor pair for 42. Stephen? 2 times 21. Very good. Now I'm going to come over to the green one. I am checking for prime. Is 210 prime? No. But is 2 prime? Yes. I'm going to circle that. That branch is now closed, and now I'm just going to work with this branch. I need a factor pair for 210. Chelsea? 21 times 10. 21 times 10. Very good. I'm going to go back to the blue one. Now I'm checking for prime. 2, prime number. 5, prime number. 2, prime number. 21, not prime. I need a factor pair for 21. Factor pair, Amani? 7 times 3. Let me pause. I'm going over to the green. Checking for prime. Is 21 prime? No, we just saw that there. And is 10 prime? No, we saw that before over there. So now I need factor pairs. We've got the 21. I don't need another volunteer to tell me that. And I've got the 10. I don't need another volunteer to tell me that. So now I'm going back to the blue and I'm checking for prime. 7, prime, 3, prime. All the branches are closed. Now I'm checking the green. 7, prime, 3, prime, 2, prime, 5, prime. All the branches are closed. What was the point of doing 2 different versions? Did anyone catch the point? What is the point, DeAndre?
To make sure that the answers are the same.
That's right. You get the exact same results. What do I mean by that? Well, we are not done. This is the work to get the prime factorization. Now we have to write the prime factorization, which means we take the prime numbers and write it as a multiplication problem. And there's a particular way to do it. You start with the smallest number, and you go to the highest number, and anytime a number shows up more than once, you use an exponent. So the smallest number is a 2, but there's another 2, and that's going to be written as 2 to the second power. The next smallest number is a 3 times 3. We're using multiplication dots. We're not using the multiplication x anymore. Times 5 times 7. And just to make sure we understand what DeAndre said, if I look at the green version, I have a 2 and a 2, 2 squared, a 3 times 3, a 5 times 5, and a 7 times 7. I get the same result. So it doesn't matter which one you do. It doesn't matter where you start. It only matters where you end up. And this is called a prime factorization. Does anyone have any questions about how we accomplish this? So now I want to be clear about one thing. This is the work. This is what we're looking for. If you do all of this and you do not write this, you will get it wrong. Last, most important part. What will happen if we multiply this out? Got 1, 2, 3, 4, 5 people's hands shot up. They do it right away. Cameron, what will happen?
You'll get 120.
You will get 420. And that is the whole point. This is equivalent to this, but it's the same number broken down into little pieces. And that's valuable because I can use those pieces to do something. You don't know what we're going to do. You're going to see it next time. Building. Okay? Tristan, yes? Yes, that's what Nali was pointing out, that this is a monomial. It's an unusual looking one, but it's a monomial. Yep, because it's only multiplication. Very good. So let's make sure we understand. And now I'm only going to do it one way. I'm not going to do it twice, and we're all going to work on this same one. So we just start with the number 102 at the top of the tree, and I need a factor pair for 102. Okay? 17 and 6. Let's see, does that work? 6 times 10 is 60. 7 times 6 is 42. Very nice. 17 times 6. So now check for prime. 17 is actually prime. 6, you should know, is not. And that can be a 2 and a 3. Prime, prime. The prime factorization for 102 is 2 times 3 times 17. Savannah?
You always have to put the smallest number first.
Yes. Now, watch this power. You can now take these numbers and multiply 2 of them, and you will always get another factor of 102. For example, 2 times 17. Can someone tell me what 2 times 17 comes out to off the top of your head? Chelsea? 34 is a factor of 102. What about 3 times 17? Anyone know what 3 times 17 is? Nali? 51 is also a factor of 102. So you can multiply these numbers in any combination. And if you look back at 420, that will also work. 3 times 7 is 21. 21 is a factor of 420. 5 times 3 is 15. 15 is a factor of 420. 3 times 5 times 7, that will also be a factor of 420. Any combination of multiplying these numbers will be a factor of 420. Does anyone have any questions on prime factorizations? Good, we seem to be doing well. Let's see how you do on your own. Find the prime factorization of 68. You've got a minute and a half. What'd you get? Start with Essence, Angela, DeAndre. What'd you get? Okay. Do you agree?
2 squared times 17.
Very good. So everybody agrees that it is 2 squared times 17. Excellent. Give me a thumbs up if you got checkpoint number 2 correct. Good. Put your thumbs down. Does anyone have any comments or questions? Because this is the point where we change things. Okay? So, that's supposed to be example, it should say example 3. I apologize for that. It should say example 3. Now you'll notice that when we hit something that involves algebra, some of the rules change. That's part of dealing with algebra, is there are some pretty complex little details that you have to know. So now it doesn't say find the prime factorization, it says factor. But it basically is the same thing. And now we're going to learn how to use a tree to break this into its little pieces. That's the goal. We want to take 12x squared y and break it into little pieces so that it looks like this. Okay? It's actually not hard at all. You just have to know what you're doing, what you're looking for. So we're going to do the same thing we did. We're going to start with the expression right at the top of the tree. But the first thing we're going to do now, since it's an algebraic expression, is we're going to split the numbers and the variables into 2 separate branches. So the 12 is going to come over here to the left, and we're going to do that as one branch. The other branch is going to be x squared y. Now I also want you to keep in the back of your mind that our goal is to be able to do this without the tree. So my really advanced students sitting here now should be thinking about that. As you go through the tree, you should be thinking to yourself, well, could I have figured that out without drawing all of this? And most of you are going to find that you very easily could. So let's start with 12. I need a factor pair for 12. Here, 2 times 6. 2 is prime, 6 is not. What's the factor pair for 6? Tatiana? 2 times 3. And so now I've got all prime numbers, so I'm done. Come over to the variables. If we have different variables, we want to split them, because actually x squared is a factor and y is a factor. So we split them. X squared was one factor of that expression, y is another. Y cannot be split any further. There's nothing that you can multiply to get y. It just is. So this branch is closed. In other words, if the exponent is a 1, that closes the branch. But this exponent is a 2. What could x squared be split into? George? X times x, because x times x is x squared. And so that's how we split that into its two factors, x times x. X is a factor, x is a factor. These can't be split any further, so those branches are closed. All of our branches are closed, and now we are done. Now we need to write it out as a prime factorization, but there's one change, so don't start writing. When we're doing an algebraic expression, we don't use exponents. And you're going to learn why next time I see you. So you're just going to have to remember this little rule, that when we're doing just numbers like this, we use exponents. When we have variables, in other words, an algebraic expression, no exponents. And you see that normally we would put 2 squared, but now we're going to put 2 times 2 times 3 times x times x times y. There is an important reason why we do this, and you'll see next time why. But just understand that that is the result we were looking for. It's just the way we do it in algebra. Numbers come in the front, variables come in the back. If I put the variables in the front, look at what it looks like. All right, we'll pause for a second as my electronic devices get their power back. That was probably not good for testing. So, all right, we're back online. I apologize. So, again, if I wrote, Essence had asked, why do we put the letters behind the numbers? If you put the letters in front, it starts to look a little unusual, where you actually instinctively should already be used to writing numbers first. And that's just the way it is in algebra. We write the numbers in front of the letters. Any questions on how we did this tree or why we got this result? All right, so let's up the level of complexity a little bit. And let's try to factor 18a squared b to the third. So, we start out, we split the number from the variables. Again, I must encourage my advanced students to be thinking about, well, how could I do all this without drawing this tree? In other words, is there a way to skip from this just to the answer over here? And I'm willing to bet for many of you, you could. Don't tell me, just see if you can do it. Maybe try writing it down right now and then do the tree with us and see if you get the same results. So now let's actually do the tree. Start with the 18. It should be pretty basic at this point. What's a factor pair for 18? George? 9 times 2. 2 is prime, 9 is not. That can be split into a 3 times a 3. That's prime, that's prime. Well, what about the a squared b to the third? What should I split that into? What should I split that into? Angela? Yeah, a squared should be one branch, b cubed should be the other branch. They both have exponents, so I know we're not done. Let's start with the a squared. We saw an x squared, so it's pretty much the same thing. What will a squared split into? Savannah? That's right. A times a is a squared. Those are both closed. But now b to the third is a little bit different, and that's why this is a slightly higher level. What will that split into? Nolly? That's right. We have a b squared and then a b. Because basically this represents 3 b's. So does this. 1, 2, 3. That's one of them. We close that branch, and now we're back to having something squared. So, write it out, no exponents. 2 is the smallest number, times 3, times 3, times A, times A, times B, times B, times B. And that is factored. That is the prime factorization. So there were a few students who seemed to indicate that they would be able to get that result that I wrote in red without doing the tree. Were you able to do it? Tristan, you were able to do it? Yeah. Annie, you were able to do it?
No, instead of doing 3 times 3, I just thought with the 9.
Okay. Okay, but you see now that it would be 3 times 3, and you got the rest of it?
Yeah.
Good. That's awesome. Okay. David? Well, it's not a big deal, but there is a reason why we're writing it with no exponents, and you're going to find out next time. Okay? Nolly?
But like when you do it in your head like that, when you try to do it like before, you should try to, if it's an even number, you should multiply it by 2 so you already have one in prime numbers. It's easy enough.
You mean factor it by 2.
Yeah.
Like this here?
Yeah.
Yeah, because that's a prime number right at the beginning, and that helps. Right. I agree with you. Very good. So let's see what you can do on your own. You may do this by making a tree or do it without a tree. Either way, it is up to you. The goal is the same. You've got a minute and a half. George, and then Adriana. Annie, what'd you get?
3 times 11 times x times x times y times y times z times z.
Okay.
3 times 11 times x times x times y times y times z times z.
So you got the same thing. What do you think, Adriana?
3 times 11 times x times x times y times y times z.
And that is correct. Very good. All three people agreed. Now I have a different question. Give me a thumbs up, and please don't get upset if you couldn't. It doesn't really matter this year. Next year will make a difference. Give me a thumbs up if you were able to do it without the tree. Good. If you use the tree, who cares? Put your thumb down. Anyone have any comments or questions? Stephen, Tristan.
Isn't it supposed to say trigonometry?
Yes, it is. You're right. Sorry about that.
I didn't do
That's fine, but you're supposed to put the smallest number first. Okay? All right, so draw a line across your paper. Your classwork is page 177. You're doing numbers 39, 41, 45, 51, 53, and 55. That is 6 questions. You've got 12 minutes. All right, colored pens up. Let's see how we did. 39 was 2 to the 5th power times 5. 41 is 3 times 5 times 13. 45 is 3 to the 2nd power times 5 to the 2nd power. 51, 3 times 7 times A times B. 53, 5 times 7 times R times S times S times S times S times S. 55, 2 times 2 times 2 times 5 times M times M times N. There were 6 questions. Make a fraction out of 6. 5 out of 6 would be a nice starting point. 4 out of 6 would be fine. For now, we just learned, so the idea is to improve. Now I'll open up the floor for questions on any of these. Questions on any of the classwork problems. Ben?
For 45, I did 2 to the 3rd instead of 3 to the power.
But 225 is not divisible by 2. You know how I know? Now, was it just a little hiccup that you accidentally wrote it the wrong way, or did you think it was divisible by 2 because you were going quickly? You put 2 as one of the factors in the tree, so you made a mistake. Any other comments, questions? Catalina?
Number 41.
Okay, what was yours?
No, 5 times 119.
Okay. 5 times 119. Okay. So it is divisible by 5, but the other factor is not 119, and the reason I know that is because if I take 119, multiply it times 5, it does not come out to 195. And you would even know that even if you just did a rough estimate, like let's round that to 120. 120 times 5 would be 100 times 5, which is 500. So, I mean, clearly it doesn't match up. Okay? So that was a little hiccup. Okay, DeAndre?
I got two comments.
Go ahead.
First of all, dual 6 questions are so easy.
Good. I'm glad you felt so.
Second of all, number 6, the answer is kind of like a tongue twister.
Which one?
Number 53.
53? Yeah, because you have to say S so many times. Yeah, it was. But I've been doing it for a long time, so I have no problem doing it. Okay, so draw a line across your paper. Your homework is on page 177. You are going to do numbers 16 through 56 even, and that comes out to 21 questions.